Today's lesson is going to be over energy diagrams. And with an energy diagram, they're a graph and they are going to look different than some other graphs that you guys have seen before. Energy diagrams are going to have an X and a Y axis. Let me show you the graph and then we're going to come back to these notes. This is an example of an energy diagram. Your Y axis is the potential energy. It's almost always going to be measured in kilojoules per mole. And then your x-axis is going to be reaction coordinate, or sometimes it says different things down on the x-axis, but you'll notice the y-axis is scaled. The x-axis is not. So the x-axis is just showing the process of this reaction taking place. There are no numerical values to be connected to that. It's just going to say the before and after. The y-axis is going to be how much energy does it take to break reactants and reform your products. So going back to the different parts of our energy diagram, what it's doing is it's showing us the change of potential energy during that chemical reaction over time. So that's the reason our x-axis just says reaction coordinate, and it's not really specific amounts of time or anything. It's just showing the changes. There's something called the transition state or activated complex, and this is where our bond breaking and bond forming occurs between our reactants and products. On these graphs, it's always the highest peak on the graph. You have your activation energy, which is going to be a really important part of Unit 5, and also in further units. It is the difference in the energy from the reactants to the activated complex. Remember that peak on the graph? And this is the energy that needs to start a reaction. This is going to tell us if this reaction is going to be spontaneous or not. Will it be able to happen and be favorable or not? Then you have enthalpy, which is represented by delta H. To find the enthalpy, remember enthalpy is the amount of energy, and we're going to do products minus reactants to figure out our enthalpy. If you have a positive enthalpy, it means that the reaction is endothermic. It's going to take energy. It's not going to start on its own. It's not going to be spontaneous or favorable. If it's a negative enthalpy, it means the reaction is exothermic, which means it can occur on its own and would be able to be favorable. And so if we look on this graph, the way you draw these is a little bit different too. So when you are drawing a reaction energy profile, you just figure out what the energy of your reactants are. So I'm just going to make up a crazy energy. I'm just going to say 300. At 300, you are going to just draw a flat line. And these are going to be our reactants. Now, for right now, I'm just going to say a generic reactants, but typically we would write what the reactants are below that line. So let's say the reactants were at 300. I'm going to say that my products are going to be at 100. So I'm just going to go some point over here on the right to where 100 is. I'm going to make another straight line. I'm going to label this one as products. And then, again, if I had an actual chemical reaction, I would write the chemical formula here. And then I'm going to say the activated complex occurs at 400. So I'm just going to go up here, and I'm going to draw another line. And this is going to be where my reaction coordinate or the activated complex is. So to draw these graphs, you're going to start at the reactants. We just sort of have a line here. It's going to peak up, and then it's going to drop down and flatline. The amount of energy from the activated complex to the reactants, so this area right here, that is going to be my E sub A. That's my activation energy. That is how much energy it takes for this reaction to start. If I were to find that amount, then I would just take the difference between these two. So I have 400 here, I have 300 here, and so my activation energy would be about 100 kilojoules per mole. Now, for the enthalpy, this line would extend down to where my products are. So I'm going to create a separate line that comes all the way down here. And this is going to be my delta H. For delta H, you always do products minus reactants. Well, I told you guys that my products, I wanted to make them be 100. I tried to make my math easy. My reactants are at 300. So that gives me a negative 200. And again, we're going to do kilojoules per mole for our unit. When you're looking at these problems, it's going to tell us how much energy is it going to take for this reaction to start. So in order for us to break our bonds for our reactants, because remember, it takes to break, freeze to form. In order for us to start this reaction, it's going to take about 100 kilojoules per mole of energy to get the reaction started. That's what the activation energy is. That's from my reactants to the activated complex. After the reaction has taken place, my enthalpy is going to be a negative 200 kilojoules per mole. And these signs matter. When we're talking about delta H, I typically always write in a plus or a minus. And so since this is negative, we go back to our notes. A negative enthalpy means the reaction is exothermic. So this reaction is exothermic, which means it gives off, it's going to release energy to the surroundings. Remember, this is all what we call the system. This is all the system. When we measure how much energy is being transferred out to the surroundings, that's what's going to change the temperature outside. And so this is going to give off a negative 200 kilojoules per mole. So let's look at a couple examples. Again, this is an exothermic reaction. We have our reactants, we have our products. If our products are lower than our reactants, then when we do products minus our reactants, it's always going to give us that negative delta H. This red part of the line is my E sub A. That's going to be my activation energy. How much energy does it take for this reaction to start? This one's going to be more than my previous one. We'll say this is 150. We'll just say that's 350 for E, so it's about 200 kilojoules per mole there. And then when you do this, we'll say this one is 50. I said this one was 150, so it'd be about a negative 100. Again, that's going to be an exothermic reaction. This one is endothermic. In an endothermic reaction, you'll notice that if I extend this out, endothermic reactions have a very large activation energy. It takes a ton of energy for this to be able to start, because it takes to break. So these reactions are not often favorable. It's going to take a lot of energy to begin them. And then my enthalpy, again, is going to be products minus reactants. Well, now my products are higher than my reactants. So if I say that these products are 150 and this is at 50, I know they're not, but we'll just make it math easier. Then I would do 150 minus 50, and I end up with that positive enthalpy, meaning that these reactions are endothermic. This is my activated complex, always the highest peak. This is where bond breaking and bond forming happens. And then you have just this generalized shape that's always going to happen on these graphs where you connect your reactants to your products. So in this one, it says, this is a question from AP Classroom. It says, which of the following best describes the changes that occur in the reaction represented by the energy profile shown? So anytime that I have these, I sort of go through and try to figure out a little bit of it. Because if we look down here, it's all talking about how much energy is transferred from the system or into the system. So I need to look at this really quick and just figure out what's going on here. So here are my reactants and here are my products. So based on the number that they're using is 25, and I would say this starts at 50. I would say that this is at 75. And so if I were going to do my delta H, remember delta H is the difference from my reactants up to my products. Then I would say that it's going to be 75 minus 50, which gives me that positive 25 kilojoules per mole. Positive means this is endothermic. If it's endothermic, energy is being absorbed into the system. Okay, so that means that it's being transferred into, remember, My first lesson, I talked about endo means into. So it's going into the system. Remember, these have a very high activation energy. And so it has to take energy for this reaction to start, because it is not going to necessarily be a favorable reaction. And so if I look at these, this says from, so that's not right. So no, this says into, but it says the products are more stable than you can't really see, but the reactants. So we'll leave that for right now. This one says it's from, again, so no. And this one says the products are less stable than the reactants. So in these reactions, when you have an endothermic reaction, because it takes so much energy to break that reaction, it doesn't really want to take place. You're having to force that reaction to take place by adding energy in from an outside source. And so because of that, your products are not more stable than your reactants are going to be. And so even though both of these, the first part is the same, that part is true, the products will not be more stable. An exothermic reaction has more stable products. An endothermic reaction has less stable products. So the correct answer is going to be D. And then another example, this is not an energy diagram graph. You need to be sure that you look at a graph at its X and Y axes to decide what you're even interpreting before you start. This is an experiment was performed in an insulated container to determine the energy changes in a chemical reaction. A graph of temperature versus time is shown. And then it says, is this reaction exothermic or endothermic? Justify your answer using the data provided. So we need to look at it and think about what is happening, because we've got to make a claim and we've got to just justify it. So in this reaction, it started at 20 degrees, and we'll just say it goes up to 40. So the temperature increased. You had an increase in your temperature. Remember, when we are measuring temperature, when you measure temperature, you are measuring the surroundings. Temperature is measuring the surroundings, how it's being affected by this reaction is what you're measuring when you're measuring temp. And so since this temperature went up, this reaction is going to be exothermic. And my justification would be because heat is transferred to the surroundings. Sorry about my terrible handwriting and that I run off the page. It's hard to write on the little tablet I have, and my handwriting's just awful. So it's an exothermic reaction because the temperature increased, and when we're measuring temperature, we're measuring that surroundings. So a chemical reaction happened between some stuff. It says an experiment was performed in an insulated container to determine the energy changes in a chemical reaction. And so when we were measuring how much heat was transferred out to those surroundings. It says a student makes the following statement. Do you agree or disagree? The energy required to break bonds in the reactants is less than energy required when the bonds form in the products. And then it says sketch an energy diagram for this reaction. And so I'm very much a visual person. So for me, it's easier to sketch the graph of an exothermic reaction and then go back and answer the second question. But you could also just think through this problem. So I'm going to go to the next slide, and I'm just going to make a quick little energy diagram. This one is going to be qualitative because I have no numbers. These temperatures are not potential energy, so do not mix that up. So I have my reaction complex or reaction coordinate down here. And then I have my potential energy. And that is going to be in, again, kilojoules per mole. And we need to think about what our delta H would be. That's how my brain works. So I know that delta H is going to be a negative number because we said this reaction is exothermic because the surroundings got warmer because it gave off heat from the reaction. So whenever there is an exothermic reaction, that means that my delta H needs to be negative. Remember, we said delta H is equal to products minus reactants. So in order for that to happen, let's just use some numbers. I'm just going to make up random numbers. So let's say my products were 400, my reactants were 100. Does that give me a negative number? No, it does not. So let's change this, and let's say that instead I flip those numbers. Let's say that my products are 100 and my reactants are 400. Would that give me a negative number? And the answer is yes. So my brain works mathematically and visually, so it is easier for me to think about these things, to be able to get backwards, to figure out what my graph looks like. Everybody's brain works different, so you might process that in a different way. So that means that my products, and I make up numbers a lot of times because they are more tangible to me than just thinking in general. So I'm just going to make my products end up being at what would roughly be 100. So I'm just going to make a line, label this as my products. Products always go on the right side of these energy diagrams. And I'm going to go to where I think 400 would be, make a line. That's going to be my reactants. And then I'm just going to make a little line up here for my activation complex. We have no clue what that number is. This is just a sketch. So I'm going to start here. I'm going to go up. I'm going to come back down to my products. So this would be a very large negative enthalpy, which is what I'm trying to get to. So I need to go back to B. A student makes the following statement. Do you agree or disagree? The energy required to break bonds in this reaction is less than the energy required when the bonds form in this reaction. And do I agree or disagree? And in this is going to be an agree. Because if I look, remember, bond breaking and bond forming happens here. It isn't going to take that much energy to break this bond as it is to be able to form it. We release. So over here we have takes to break. Over here is takes to break. Over here is freeze to form. So for takes to break, it's going to take energy, but it doesn't take that much energy. If this is 400, we'll say that's 500, but it is going to free a ton of energy over here. So the question is, the energy required to break the bonds in this reactance is less than the energy released when the bonds form from the products. And that is going to be, I'll just write it over here for letter B. I'm going to say agree. And I'm going to say because the reaction is exothermic. In order for it to be exothermic, that means this is literally the definition of an exothermic reaction. It has to take less energy to break the bonds than to form them, because that's how it gives off that energy in this reaction. Whereas if we look back over here, this one, it takes more energy for an endothermic reaction to happen than it does to release. That's the reason it's endo. It takes energy from the outside, from the surroundings, whereas an exothermic reaction releases that energy to the surroundings. So hopefully this helps. We're going to see more complicated energy diagrams as we continue in this unit. This one only shows with just one set of reactants, one set of products. Sometimes we're going to see that it gets a little bit more complicated than that. You want to get really comfortable with this and figure out a way that you are confident about how to draw these. Everybody's going to think about them differently. I'm just very much a math-minded person, so it helps me to make up numbers to be able to have visuals.